In the previous lessons, we defined three coordinate systems: Cartesian, cylindrical, and spherical, along with their differential elements. Now we need the tools to describe how fields change in space. In this lesson, we introduce three fundamental operations of vector calculus: the gradient, the divergence, and the curl. These operations use the del operator, written as an inverted triangle nabla. The gradient tells us the direction of steepest increase of a scalar field. The divergence measures how much a vector field spreads out from a point, and the curl measures the rotation or circulation of a vector field. The gradient operates on a scalar field and produces a vector field. Given a scalar function f of x, y, z, the gradient is defined as nabla f equals partial f over partial x, x hat, plus partial f over partial y, y hat, plus partial f over partial z, z hat. The gradient vector points in the direction of the greatest rate of increase of f, and its magnitude equals that rate of increase. Geometrically, the gradient is always perpendicular to the contour surfaces of constant f. A simple example: if f equals x squared plus y squared, then nabla f equals 2x x hat plus 2y y hat. This points radially outward from the origin, which makes sense because f increases as we move away from the origin. In cylindrical coordinates, the gradient has the form partial f over partial rho hat plus 1 over rho, partial f over partial phi hat plus partial f over partial z hat. In spherical coordinates, partial f over partial r hat plus 1 over r, partial f over partial theta hat plus 1 over r sine theta, partial f over partial phi hat. Notice how the metric coefficients appear in the denominator. The divergence operates on a vector field and produces a scalar. For a vector field A with components A, x, A, y, A, z, the divergence is defined as nabla.A equals partial A x over partial x plus partial AY over partial y plus partial AZ over partial z. Physically, the divergence measures the net outward flux per unit volume from an infinitesimal region. A positive divergence means the field is a source at that point. A negative divergence means the field is a sink. Zero divergence means the field has no net outward flow. It is solenoidal. For example, the field A equals x hat plus y hat plus z hat has divergence equal to 3, meaning it uniformly expands everywhere. In spherical coordinates, the divergence formula becomes 1 over r squared partial over partial r of r squared ar plus 1 over r sine theta partial over partial theta of sine theta a theta plus 1 over r sine theta partial a phi over partial phi. The divergence will be essential for Gauss's law in electrostatics. The curl operates on a vector field and produces another vector field. It measures the tendency of the field to circulate around a point. In Cartesian coordinates, the curl of A is computed as the determinant of a 3x3 matrix with x hat, y hat, z hat in the first row, partial over partial x, partial over partial y, partial over partial z in the second row, and ax, ay, az in the third row. Expanding this gives three components. The x component is partial az over partial y minus partial ay over partial z. The y component is partial a x over partial z minus partial a z over partial x. The z component is partial a y over partial x minus partial a x over partial y. Physically, a non-zero curl means the field has rotational behavior. A field with zero curl everywhere is called irrotational. The curl will be essential for Faraday's law and Ampere's law. Two important identities connect these operations. First, the curl of a gradient is always zero. That is, nabla cross nabla f equals the zero vector for any scalar f. This means gradient fields are always irrotational. In electrostatics, this tells us the electric field E equals minus nabla V has zero curl. Second, the divergence of a curl is always zero. That is, nabla dot nabla cross A equals 0 for any vector A. This means curl fields are always solenoidal. In magnetostatics, this tells us the magnetic field B equals nabla cross A has zero divergence. These two identities are not coincidences. They reflect deep geometric properties of space and will appear repeatedly in Maxwell's equations. Let's review. The gradient takes a scalar field to a vector field pointing in the direction of steepest increase. The divergence takes a vector field to a scalar measuring the net outward flux or source strength at each point. The curl takes a vector field to a vector field, measuring the rotation or circulation tendency. Two key identities, curl of gradient is 0 and divergence of curl is 0. These three operations, together with the two identities, form the mathematical language of electromagnetic theory.